We've learned how to look at the parent function. We've learned how to move graphs. We've been able to see the difference between a power function and an exponential function for it. Remember, power functions have a value and then it has x to some power, right? Had x to some sort of power. So this never changes. And then we've had exponential functions where we have our value and we have a set base raised to a changing power, correct? So we've had a couple of different instances of different types of functions where x is both on the ground, x is in the air, things like that, okay? So the difference, as I have it here, power functions increase by the same amount every single time, right? So if this was a 2, every single number would be squared, okay? When we had our exponential functions, we're increasing by 1% because our base is what's changing, okay? The important part is that as we look at a graph, or if you're in business and looking at sales or whatever, we have always been finding the answer for x, right? We've been plugging in an x value, knowing what our x value is, and then finding the corresponding y value. So we basically have been going one direction. What this now allows us to do is now we can pick values over here on the y, and we can answer questions of where they actually fall on the x axis. So now we get to go back and forth both ways across our graph, which is what we have been wanting to do. So if we're dealing with graphs, as we have been dealing with graphs, how can we now write a function, write a model, when we only have the points? So before I've been giving you guys the actual formula and saying, hey, it's modeled by this, find the x or y value. So now what happens if you have a whole bunch of points and you need to figure out what is the exact equation for it? So we are going to work through how to find that. And just like with linear equations, we needed 2 sets of points to graph any line, correct? Because 2 points gives us the slope of the line. 2 points also, we can then plug the slope in with point slope and we can find the equation of the line. So 2 points will help us graph a line. 2 points and 3, like if we had the vertex and then another point, we could graph a quadratic equation. And then we can now also, using 2 points, come up with a plan to get a power or an exponential function. And to do that, we're going to use something that we've already learned how to use, systems of equations. So remember back when we had our 2 systems of equations, we could use substitution, we could use elimination to solve them, and then we even went into systems of 3 equations and worked through that. So when we have 2 points, we can make 2 equations with 2 unknown variables. Remember, our number of variables that we have determines how many equations we have to solve it. So in this case, we have 2 unknowns. We have an a that is an unknown. This is our y-intercept. Often it's our constant of where we're starting. And then we have our b value, which is also unknown. And that's your rate of change. So one of the formulas that you'll need to know, or 2 of the formulas that you'll need to know for your test, are your interest rate of change. How did we take those these are our parent functions. So when we talk about parent functions or our basic function, this is what your basic function looks like. So when I say write the parent function or write the basic function, it's these 2 for this, okay? And then we learned that we could change that rate, right? So an amount, if we were looking specifically interest, gave us our principal, right? Which was the amount that we start with. That would be our A value, our principal. And then we had our rate, 1 plus whatever whatever your percent rate was, times how many times you're compounded. So this was our regular interest rate, right? We like it if it's added. If it was added, what kind of equation was this? Growth or decay? Growth, right? It's getting bigger than 1, so we're growing. If this was subtracted, it's decay. It's less than. Does that mean this is negative? No. So growth meant we needed terms that were greater than 1. Decay meant we needed terms that were between 1 and 0. Right? What was the n value? Who remembers what n was? Correct. The number of times that you are compounding. Right? So if you're only compounding once a year, this number is 1 and it doesn't even exist on the bottom, right? But if we're compounding quarterly means 4 times a year, we would divide our annual rate by 4. But then we'd also have to multiply the number of times, so that's why we have it up here. So we had 4 times the time that we have, right? There was a special one that we learned for continuously compounded. So as this n approaches infinity, and we go from daily, which was 365, to hourly, to seconds, to nanoseconds, and it's compounded continuously, this section turned into our E value, correct? So our principal stayed, but instead of these different parts, we had our E value times our rate, raised to our rate times time. And this is our continuously compounded equation. What did we say is the guesstimate value for E?
It's like 2 point something.
718. 2.718 is our guesstimate value for E. E was also special because when we decided to start using logarithms, if we had a log specifically of E, did we call it log of E? No, it has a special name called the natural log. E is Euler's number. Okay. So these are all some important things to know for it. So if we have all of this information, we learned logs, we learned our log rule. Last week we learned how to expand and condense logarithms with matching bases or maybe with an exponent or a coefficient in front. So how do we use all of that to come up with systems of equations? Okay? So if it says write an exponential function for a graph that passes through the points 1, 6, and 324. So I've got this graph, and I've got 1, 6, and I've got 324. Okay? And I want to know what is the graph that passes through. What is the equation? This is not a line. It's exponentially growing. The very first thing that we're going to do is decide where do we start. Okay? Exponential function. It tells me write an exponential function, so I'm going to start with my exponential parent function. Right, that's a good place to start for it. And then it gives me 2 points. These points here are our x and y values. They are x and y, and I have 2 different ones. So we can write 2 separate equations. So what we've done here in the first one is we're going to set up our 2 different equations. Remember, x is 1, y is 6. So I'm going to plug in the y. I try to color code it. Y here, we're going to write a, b, and then raised to our x. Our x is 1. Everyone follow me there? So there's 1 from our first point. We've got 24 equals ab to the 3rd from our second point. Okay, now we have 2 unknowns and 2 equations. So we can solve those using substitution. Now the number one rule of substitution means you rearrange one equation and you plug it back into itself. No, you rearrange one equation and then you use that equation and plug it into the second one. If you make the mistake of plugging back into itself, you will get infinite solutions. Okay? But then when you go back to check it, it's going to be wrong. So the easiest one to rearrange, if I'm looking at both of these, b raised to the 1 is simply what?
1 or
B.
yeah.
Okay, that is something to know. Anything raised to a 0 is 1. Okay? So this one, I'm saying this one's pretty simple. I'm going to solve for a. So we just rearranged a, and we've got a is equal to 6 over b. Everyone following? Okay. So if a is 6 over b, I'm going to take it, plug it into my second equation. I've got 24 equals 6 over b times b cubed. Now we just get to simplify it. We can use our quotient rule, right? We've got b cubed divided by b. 3 minus 1 is 2. So we have 24 equals 6b squared. We're just going to keep using our rules that we know. This is where we're pulling everything out of our toolbox. So 4 is equal to b squared. We're going to take the square root. What is something that I didn't do right here that typically we would see right in front of this? If I take the square root of a number that wasn't already squared, what do we usually put? Plus or minus. Excellent. So typically we would put plus or minus here, but since we are finding a b value, what did we learn about our b values? Our b values need to be positive. It's okay if they're a fraction, but they need to be positive. So we're going to take the positive term. We're not looking at a negative growth. We know it is growing, so we need it to be positive. Okay? So b equals 2. So we've got that solution. Now we're going to go back to our a was 6 over b. 6 divided by 2 is 3. So now I have an a value. So now we get to go all the way back to our exponential equations initially and say a was 3. So I'm just going to plug in 3 where I see a. B is 2. And I rewrite it with my variables x and y. That makes sense how we got there? Okay. Not super hard? Okay. All right. Let's do one more example of that. What if we have 1, 4, and 2, 12? Okay. I'd like for you to write out the 2 basic equations on your boards or in your notes, either way. You can use your notes on the test or your homework. So write out the 2 equations that we would have initially, and then we'll work those through. We're doing this, I'm telling you in advance, it is an exponential equation, an exponential function. What we find when we've got these exponential ones is initially we were having to do logs and lots of things for this. Now that we have real points, these are the easier problems to solve. We're going to use our tools in our toolkit whenever we move over to power ones. Okay. So everyone should have for their first one, 4 is equal to b, a, b to the 1, right? And 12 is equal to a, b squared. Everyone have that for their first ones? Okay, so let's solve this first equation for a. A is going to be 4 divided by b. We're going to plug that into equation number 2, and we get 12 is equal to 4 over b times b squared, which simplifies to what?
4b.
4b. So what does b equal?
3.
B is equal to 3. Excellent. Now we're going to work backwards, so we just kind of make ourselves a circle. And A equals 4/3. So now we have both of our values. We go all the way back at the top, and we say y is equal to 4/3, 3 to the x. All right, any questions about these steps here? This is just using our exponent rules that we've had, our process of substitution with 2 equations to solve for our variables. So as long as you keep your steps in order, solve for one, plug it into the second. I say it kind of makes a circle. I work down one side and then I just back it on up. I like to write them side by side on my work versus up and down, because it does allow me to work down and just kind of work in a circle and see them next to each other. If you work them horizontally and across, you can figure out your own system for it. But if your mom's checking homework, I do have them side by side. All right, everyone get this? Okay. So, these seemed pretty simple. We know how to solve for those b's. Nothing came up very complicated. Let's look at when we have a power function now. Okay, so now that we have power function, we're going back. Our x and our y are both in the bottom. They're actually on the line. And we have our a and b that are raised. We've got a raised to an unknown. And we're trying to find those unknowns. And now we have an unknown in the exponent. Okay, so we're going to use the exact same steps. We're just going to use different tools that we've had out of our toolkit. Most of the ones that we have learned here in chapter 8 about logarithms. Okay, so we're going to solve it the same. We're going to set up our equations the same. And we're going to step through what do we know. Okay, so we have an equation and we say it's a power function. It goes between 2, 5 and the point 6, 9. So the very first thing we're going to do is write our parent function and then set up our 2 equations below that. Right? It is valuable to go ahead and label your points x and y. It is very easy to get them confused and put them in the wrong place. So if you go ahead and label them x and y, that's just another step that can be helpful. So we've taken 2, 5, and we've plugged it in, and we now have 5 is equal to a times base 2, so because that was our x value, right, raised to some b exponent. And we've plugged in 6 and 9 on the right side. Everyone agree with step 2? Our equations? Okay. So again, we are going to solve one equation for one variable. Can be anything that you want, but if I'm solving, A is a lot easier to solve for right now. So it's okay to pick the easiest. Your answer will come out the same either way. But we've said A is equal to 5 over 2B. So we're going to take that A value and plug it all the way into this second part. So I have 9 is equal to 5 over 2B, because that was my A place, times 6 to the B. Now this is not something that we have technically talked through. So I have a little orange bubble over there on the side. Okay, so what does it mean when we have 6 raised to a power divided by 2 raised to a power? How do we simplify this? Because we know how to simplify things if they have the same base, we would just subtract the exponents. But these don't have the same base. I can't even make them have the same base. So logically, how could I simplify this? Well, for me, initially, there is a rule for this, but I'm going to think through how do I actually get there. What does this really mean? Say, and I wrote down here 6 squared. Say I change my b, for this case I'm going to do cubed. Okay? Change it to 6 cubed. What does that really mean? That really means 6 times 6 times 6 over 2 times 2 times 2. Are we in agreement that this is what it's like if we spread it out? Okay. If I take each of these fractions, 6 divided by 2 is 3. 6 divided by 2 is 3. 6 divided by 2 is 3. And I have the same amount of them as what I started with in the first place. So I really have 3 cubed. All right? So when we have constants, these integers, raised to the same power, we can simplify the integer part and keep the power. Okay? So versus me just saying, oh, 6 divided by 2 is 3, and you just keep the b, this is why it works. What we have done is we are really separating out into, 3 sets of individual fractions, or in this case, 2 sets of individual fractions. Yes, sir?
Yeah, so on the question, like you're multiplying, but then on number 5, it's like, so it's 5 over 2b times 6b, but then it's 9 equals 5 times 6b over 2b. It's like how you
Like the 5 and 6 just switch places and
Because this is all multiplied. So, if I had 1/2 times 3, is that really 3 over 1? Okay, so that could be the same as 3/2.
yeah, but you multiplied the 3 and 1. That's a 5 and a 6. That wouldn't.
I just haven't multiplied them yet. Because they're, okay. From this one, let's do this one. 5 over 2b times 6b. This 6b is really over 1. Okay? I cannot simplify 5 and 2b. And by the power of commutative property, I can switch those. So this is the same as 5 over 1 times 6b over 2b. Follow me here?
Yeah.
Okay. 5 over 1, I can simplify. They are both integers. So that simply becomes 5. Now that I have 2 integers raised to the same exponent, this part can be simplified. Which is this little step that I'm showing and that we were just talking about. When we have integers raised to the same power, what we can really do is separate it out and say, let's simplify the integer portion of it, and we keep the power. So 6 divided by 2 becomes 3, and it stays to the same power. Does that make sense? So remember that this is multiplication, which means that they can move, they can commute the same. And so what I did is I paired up the 2 that can be simplified. Just moved it over. Any other questions? How we got down to now 5 times 3 to the b? All right. So we're still solving for b. We have 9 is equal to 5 times 3 to the b. So we want to solve for b. We got to get b by himself. The first thing is we can go ahead and get rid of that 5. We can divide both sides by 5. So I've got 9 divided by 5 equals 3 to the b. Right? Now when we're solving for the top, for that exponent, we use logarithms. Right? The opposite of an exponent is a logarithm. So we can either take the log of both sides. We can use the log rule. There were a couple different ones. You could raise sides to powers. Okay. If we took the log, I'm going to rearrange it this direction. If we log roll, remember we start like this. So we have log 3 9/5 equals b. Okay. This would be valid to solve for b. Well, you could also write it without the log rule. Let's write it here. Take the log of both sides. So we're going to take log 3. Remember, when we take a log, we get to choose what base we want to use. So I'm going to use 3 because I have 3, because there's a special rule that says when my log base and my equivalent value base match, then the answer is just the exponent. So if I take the log 3 of both sides, on this one I have base 3, equivalent value 3, this matches, the whole thing goes away, and I have b is equal to log 3 9/5. We've got the same thing both ways. So 2 different ways of looking at it, we get the same answer. Okay, I want to use my calculator. We can't use our calculator because we have a 3 on the bottom. So there was that change of base formula that said we're just going to put that division line right through there. 9/5, we can go ahead and use our calculator and get 1.4, 1.8. In that? Yeah, 4/5, 1.8. And so say that we've got log of 1.8 over log of 3. Punch this into your calculator. Log 1.8, it will give you a decimal. Log 3 will give you a decimal. Use 3 decimal places. And then divide, and it will give us approximately 0.535. So where does that all get us? Because we've done a whole lot of work. What did we really just solve for? We just solved for b. Okay, so all of this is equal to b. Well, b is only part of our equation. We've got to go back and find out what did we have for a in the very first place. So we said that a was 5 over 2 raised to the b. We now know that b is 0.535, so we're going to take our calculator and use the x to the y power. So we're going to plug in 2. We're going to hit this x to the y power button and then plug in 0.535. And it will give us a decimal. And then we do 5 divided by that and we get our a value. Now that we have a and b, we can go all the way back to our power equation. Plug in a, the 3.45, and plug in b, our 0.535. So these are not as clean. These are a little bit messier. When you keep your steps in order, it will help keep that cleaned up. Right? Let's do another example. Okay, so given the points 2, 1, and 6, 5. Okay. write the power function that goes with these points. So initially I'm gonna say x and y, and we're gonna write our two equations. So our first equation is 1 equals a times 2 to the b. Our second equation, 5 equals a times 6 to the b. All right, what one do you guys want to solve for first? Left or right? Left, okay? So a equals what, Joshua?
Which one?
This one.
A equals 1 over 2b.
Perfect. A equals 1 over 2 to the b. So we're going to move him sideways and plug him in. I got 1 over 2b times 6b. Can I combine these? Can I simplify this? Fraction, this is really 6 over 1, correct? So I can really just say 6b over 2b. Everyone okay with that? 6b over 2b equals what? 3 to the b. Perfect. So now I have 5 is equals 3 to the b. Now I have a variable in my exponent. How do we solve for that? We use a log. Okay? So we can take the log of both sides, or we can use the log rule. What would you like? What? Take the log, okay. So we're going to do, what log would we like to take? What base? Base 3, perfect. So we're going to do log 3 of 5 equals log 3 of 3b. Log 3 of 5, I can rewrite as log 5 divided by log 3, correct? And log 3 of 3 to the b turns into
B.
just b. Our base and our equivalent value match, so our answer is simply the exponent. Now we get to use our calculator. Log 5 is 0.699. Log 3 is 0.477. So we're going to say this is approximately, which is usually the little squiggly lines, 1.465. That's B. So where does this 1.465 now go?
1 over 2b.
Goes right back up there. So now I have 1 over 2 to the 1.465. Which gives me 2.76. And gives us 0.362. So now I have A and I have B. So we're just going to go back to our parent function and plug in A. A is 0.362 times x to the 1.465. All right, do you feel comfortable doing three more homework problems each of these? You can know the steps of it? Okay.
How would that help us?
What?
How would that help? Like
So what you will find, this is just important to know how to solve an equation. Where this is kind of the wrap up of using all of the rules that we've learned about logarithms together. Mostly this goes into business. If you're going into business, you'll see it long term. But if you have a whole bunch of data, and I'm going to go over that just so that we can kind of talk about it. If you have a whole bunch of data and you're a scientist or you're in business and you're gathering a bunch of data and you have all of this and you're like, I'd like to see a trend. What direction am I going? Can I expect? Can I predict for the future? Maybe how many sales I'm going to have if I keep going at this rate. Is something decaying if you're looking at science, if you're looking at like growth of bacteria or maybe decay of something. So you've got all this data and you have to compile it. And this is where this all kind of ties together. Like I said, we have to know how to go from one thing to the other. We can't always be given this. A lot of times what we have is we just have data. We've been given data. And so it says, how do we figure out what type of equation it is? So when you've got data, you're also looking at it and going, I don't know if it's a power function or if it's an exponential function. Is it growing by the same amount every time, or is it growing by the same percent every time? Those are two different function values for it. So there's a special way, and we're just going to talk through it. You don't have homework on this one for it. But if you have a bunch of data and you look at it and you start plotting it and you're saying this does not fall in a straight line, or if you're looking at the jumps, like the jump between 1.6 and 2.7, initially it's 1.1, now our next jump is 1.7, then it's 2, then it's 2.5, then it's 4.2. This looks like it's increasing, and it's starting to maybe increase by some sort of power or exponent along here. So where is it going to be maybe when we're at 20? What are we looking at? So our jump is increasing, but it's not linear. It's not by a set slope. And so it's got to be by something else. So if we are going to check for an exponential pattern, there's a special way where we can take the natural log of all of the y values and rewrite them. So I just rewrote them underneath here. So I took the natural log of just the y values. So that's just plugging it into my calculator. Finding these new values and plotting the new points. So my x stays the same, my x values stay the same, but my new values are my y. If it now forms a straight line using the natural log, then your data falls into an exponential function, and you can write yourself an equation for that. Okay, so that it's a good way to be able to look at data and say, what is the trend? What can I predict for it? Now, if you're doing your data and you take the natural log of the y values, and I put a picture down here of what these actually look like, and they're still not a straight line. What does this look like? Does this look like in inverse function when we were doing? So this is a logarithm graph. You can then choose to take the natural log of both of them. So whenever we did just the y and we plotted it, it still looked very much like a logarithm curve. If we take the log of the x and the y and we go ahead and graph it, and here was the original ones. Now these are the new ones where they're plotted with the natural logs of both, and it becomes a straight line. Okay, then it's a power function, and you can use the power function to find your data. So again, these are the rules and the ways in which we can go from someone has just given you data, whatever it looks like, and you're trying to figure out where does that go? Can I write an equation for it? Can I have something where I can predict in the future? Is that helpful? And they also have calculators that do all the work now too. Yeah, which is good. It's good to know how to do it. Okay, so mostly for the wrap up for 8.7 is the value of doing these. There's 4 homework problems for each of these. Is all there's on that. Okay, the value of doing that, and I did one for you already. Is being able to use all of our tools in our tool belt to be able to look at a set and say, what do I know? And that's what we've talked about from the very beginning of the year, correct? Like, how do we take what we know to solve what we don't know? So if I'm given 2 points, what do I know? I can write 2 separate equations. I know how to use substitution to solve for a set of equations. I know how to rearrange and solve for a variable. Now to solve for that certain variable, I might have to use exponent rules. I might have to use logarithm rules. So this is a great wrap up of using all of the tools that we've had in our tool belt from multiple chapters to be able to finally come up with a solution. Right? Okay, logistic growth. Okay, what to know about logistic growth? I just said up here, like sometimes if you have an environment, like it would be nice to think that everything would always expand or always grow in its best terms. So if you are growing bacteria, that you're gonna get a perfect growth rate the entire time. Or if you have a control situation set up, or if you have a bank account that like there's never gonna be a cap on how much that you can earn. Unfortunately in life that doesn't always work that way. Sometimes we have bounds. Sometimes there's some boundaries, like if you're growing bacteria in a petri dish, like it can't grow outside the dish, right? So the area that it can encompass is only a certain amount of area. Something that's interesting is my best friend just went into the hospital for labor this morning. And so I thought of that. I was like, oh, there's only a certain amount of time that a baby can grow inside a mom before like there's a bound that it can't cross anymore. Right? So we all have these different bounds. You might have a bank account that says, we will pay X amount up to this threshold. And then at that threshold, it's going to be something different because they don't want to pay what it would cost them outside of that. So when we have a threshold, we have a logistic growth equation. Okay, so logistic growth is a graph that looks, not down, looks like that. Okay, it has both increasing areas and decreasing areas. You see how they're combined together? And there is a special point, I like to call it our turning point. It looks like a cubic equation. And there's this turning point of where you have maximum growth. So we're growing, and at this point, you have maximum growth. This is very valuable if you go into any business field and you are looking at maybe increasing prices for increasing profits, or maybe you've got storage or you have supply chain issues, and there's a point where you're like, oh, well, if I do this, it's just going to keep growing. There will be a turning point to where what your very next increase will be less than it was before. So you've got a point of maximum growth before you start tapering off. They use those words a lot in business. It'll start tapering off. Okay? So our logistic growths are bounded by 2 separate asymptotes. One asymptote is always going to be the x-axis. The other asymptote up here, according to the equation, is going to be a y equals value, right? It's y equals because it's a horizontal line, correct? And our turning point will always be exactly halfway between the two. Right? So the equation of it looks like this. Y equals C. C is your upper asymptote. It is your y-intercept. Or not your y-intercept, your y asymptote value. Okay? Divided by 1 plus a times e, the negative rx. You do not need to have this memorized. Okay? But when you see this, we need to be able to look at a graph and say, if I have a graph that has both growth, some growth area and some slower growth area, that my upper asymptote is my C value, okay? And then where would my y-intercept be? What question do we ask for our y-intercept?
That's a 0.
When x is 0. So if x is 0, this whole thing turns into what? 1. The number 1. Right? So then my y-intercept is simply c divided by 1 plus a. Okay? And that's just a practical when x equals 0. So we've got our y-intercept there, and I think I have a picture. So these are some pictures. So let's just look and see what we can figure out. For this first one, where is my upper asymptote on the first one? 4. So what graph does it have to be? C. Because it goes to 4. Right? Where is my upper asymptote here? 3. So it would have to be, okay. And my upper asymptote here? So it would have to be B. That's pretty easy. You guys figured that out without knowing all the other numbers. Right? So if we looked at it here, what would be my y-intercept? If x equals 0, this entire part turns into the number 1. So my y-intercept is
2.
4 divided by,
Oh, 3.
4 divided by 3. So 4/3. So on this one, we're about 4/3 right there. Okay, that's not your turning point, but that is, your turning point here would be found at y equals 0. Okay, and at that is where we need to use our logarithms. Because if I know that my turning point is found at y equals 2 on this one, I would need to plug in 2 and solve for x, and x is in an exponent, which means to solve for this x, I have to use natural log. All right, do we see how now that we have a value, we would need to use our toolkit to find our x value? Got it? Okay. So that is logistic growth. If you go into business, you will see that a lot more. But that also wraps up chapter 8. Let me look. Okay. If you are given if we are given this equation, what is its parent function? Is this a power function or an exponential function?
That's power. No, it's exponential. My bad.
It's exponential function because our x is in the exponent. This is an exponential function. So it goes off of our base. Here's our parent function. Okay. What is our a value? 5. So here's our a value. What's our b value?
3.
Okay. What does that 3 mean? What does the graph do?
Slope or rate of change.
It's the rate of change, so each time it's doing what? There's a word. Starts with a T. Triples?
Triples.
It's going to triple. So this graph is tripling every time, okay?
Yep.
So if I asked you, what is the h value? What is our h value?
It's either 3 or 2.
Positive 2.
Wow.
Excellent. What is our k value?
Yeah, just a
Negative.
Positive 3 is a k value. What does h and k do?
yeah, moves the graph.
It moves the graph. So if I have my initial base function, if I say to graph my base parent function for this, I would be graphing 5 times 3x, correct? That would be what I would graph initially. So when x equals 0, y equals 5. Right? We're going up like that. When x equals 1, y equals what? When x equals 1, y equals 15. Okay? So here's my base one. And h and k do what to this graph?
It moves it up and down.
Moves what? So this 0, 5 moves how, according to h and k?
Up to right 3.
Up 3. K is our y. So we're going to go up 3. 1, 2, 3.
Over to the left, or right.
To the right, it's positive. 1, 2. So our point here is now translating here. And the same for this one. It's going to go up 3 and over 2. And that will be our new graph. Right? So our h value moves us along the x-axis. Our k value moves us along the y-axis. Okay? What is the asymptote for this?
The x-axis.
What is your new asymptote? 3. Y equals 3. So if in my base one, my asymptote is y equals 0, right? It's the x-axis. I have moved my entire graph up 3, so my new asymptote lies along y equals 3. Should an asymptote ever be a number, or should an asymptote always be written like a line? Like a line. That's right. Okay? So what is the domain of this graph, or of this function?
All positive x.
All positive, because we're using up all of our x values from left to right. What is our range?
So you're still on positive.
Is it all positive? Can I use the number 1? Where's my new asymptote?
You can't go under 3.
I can't go under 3. So my range is y must be
Under 3.
greater than 3.
Yeah.
So my range is always affected by my asymptote.
Why is it not greater than or equal to
Because it always approaches the asymptote, but it never ever touches it.
3?
So we can't use the equal sign, it will always just be greater than.
But it touches it right there.
It looks like it does, but it technically doesn't.
Oh,
Pretend like it doesn't. Okay, so it gets really, 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 really close, but it never actually touches your asymptote. Okay, so is this a growth or a decay? It's growth. Excellent. Okay, if you wanted to find one more point, another valid point, what could you do? What would you do first? Plug in a value for x. Say you wanted to find the point at x equals -1. You would plug in the value for x and solve for y. Could you guys do that?
Sure.
Okay, that's what it means when it says find one more valid point. Your pick. Okay. Could I plug in,
I'll just choose 2.
what?
Hmm?
2? Yeah, you could use 2. That would be the smart one to use, right?
We'll make 3, 1.
Because it makes this in, if we plug in 2, why would he say to plug in x equals 2? Because it makes it 0 and this whole thing goes away. And all you have is 5 plus 3. 8. You don't have to do a lot of work, a lot of calculator work for it. Good choice on that one. Okay? Let's see. We need to know how to simplify still. Simplify with exponents, so make sure you know your exponent simplification rules and how to rewrite logs. If it is already written with logs, should your answer have log in it? No. If it's not written with logs, if you just have that, then you're going to rewrite it as log.
5, 9x.
There you go. Okay. So when you're simplifying or rewriting, that's what you'll need to do for that. Inverses. Remember, what were our inverse? If I have, what was the inverse of that? Correct? Okay. Make sure you know your inverse rules. That was from homework this last week. You'll need to know how to do your inverses and how to condense and expand logarithms. All right. Any other questions on chapter 8? Ready to take a breath? Okay. Can stand up, stretch, whatever. Remember, your test is open notes. Feel free to use them.
So we have this homework and the test this week, or is the test next week?
The test is this week.
Okay.
So you only have 8 homework problems, and then the test, and then we'll see if I decide to give any homework for this next chapter. Please no. Well, I hate like then having a week where you have a ton of homework. That's not fun. Never fun.